This is a quick video to show you how to use GDB for doing some debugging, and I'll discuss how we use it for segmentation faults and how you can print out the contents and type of a variable by setting breakpoints in your code. And I'll get into that in a moment. I'll start off with this file that I have, which is called broken.c. Now we can see that I've declared an integer pointer called b, and I never gave it an address to refer to, meaning that when I try to put the 10 into b, it should cause a segmentation fault because I don't have access to that memory. Now, compiling as we normally would, I'll just give it some output name and tell it the file that I want to compile. It compiles okay. If I compiled with the warnings flag there, it would tell me that I've used a variable uninitialized, but it doesn't matter. So if I run this, we should get what I expect, which is a segmentation fault core dumped. These are particularly hard to fix because I got no information about where this occurred. If my program was much longer, I'd have to understand which section of the code it occurred in simply by reading what happened up until that point. But in this case, I get no hints at all. So what we do for this is we recompile, but we just add this extra flag on the end, -g, which asks it to keep in some debugging information. So if I recompile, nothing seems to have changed, and if I run it again, nothing seems to have changed there. But I do have the ability now to run it inside GDB. I do that by typing GDB and then the name of the executable. So I called it broken here, so that's what I'll be using, broken. And it started. So GDB is running, but my application isn't. If I want to start this running inside GDB, I just type run. And that means run whichever program I gave you on this line. Once I do that, it starts the program and we get the exact same thing, segmentation fault. But in this case, we've got a bit more information because GDB has asked for some of that information from it. So the first thing you see is that it has the memory address of the variable that caused the problem, which is b in this case. It tells you which function it occurred in which file that function exists, and in which line of that file. And it even gives you the contents of that line. So we see here, in broken.c, in the main function on line 5, we have *b equals 10. So we've dereferenced b and tried to put 10 in there. And that's what's caused the problem. There are a couple of extra things you can do to clarify the problem. In some cases, you won't really get this much information. So then you can just type bt, which kind of propels you backwards through all of the functions that have been called and tells you what's going on there. Or you can type where, and it will tell you which line number it occurred on. In our case, all of this information was already in this first section, so bt and where didn't help at all. You can additionally ask to print out some information about the variable. So we only have one variable in this whole program, which is b. If I type print b, it tells me that b is an int pointer and its value is 0x0. That's the null pointer, that's pointing to an invalid location in memory. So if you see a pointer pointing to this address, it means that it was uninitialized. And we know that's what it was. So we've just figured out the problem with our code by using GDB. That's how to resolve a segmentation fault. So I'll quit out of this and I'll try another program that doesn't have a segmentation fault. So if I look at this other one, broken2.c, this one may have some logic error. We don't know. Doesn't really matter for this example as long as we understand how to get to the bottom of it. So all I'll do is I'll compile it again, remembering that when we do compile, we have to do GCC or CC, it's up to you. And we have to remember this -g flag to give some more debugging information. So now I'll do the same thing again, GDB, but this time broken2 is the name of our program. Press enter. Now, what I want to do in this is I want to stop the program at a certain point so I can observe the state of the program. So what I'll do now is I will set a breakpoint at line 5, which means when you reach line 5, pause the program and let me control it. So if I type break 5 and press enter, it just tells me that we've registered a breakpoint in that file, line 5. All good. If I type run as before, now it will stop at line 5. It says we've encountered breakpoint 1 on this line. So when I print out the contents of A here, if I do print A, we have this weird number. This is just a sign that it's uninitialized. It's some, garbage value that's in memory. So what we should learn from this is that pausing at a line means that it pauses before the execution of that line. Because if it were pausing after line 5, A would hold the value 31, but it doesn't. It holds some tiny, tiny number. So from here, I could type continue to continue the program, and it will go until it reaches the end or another breakpoint. Or I can type step, which means take one step to the next line of code, which it will do. Now we're on line 6. So if we do print A again, hopefully the value of A will be 31. So print A says it's equal to 31. Perfect. So that last line worked exactly how we expected. And if I do step one more time, we will execute line 6 and move to line 7. So after this calculation is done, we should have 31.4. We can see that's a precision error with floating point. What happens if I print out C right now? We should expect to have some garbage value, which we do, some tiny weird number. And if we take one more step, we should have that C after this is equal to A on 2. A at this point was 31.4. So if we print out C, we can see that's equal to 15.7, more or less. So that's all going well. And now we can just type continue to let the program continue execution as normally, and the program's finished. So when you're finished with GDB, you just type Q and enter to exit it. And that's it.